Let's compare the focusing power of using all 64 elements in your probe. We'll compare that with a 32 element aperture and a 16, and we're going to use a 64 channel OmniScan X3.
Fascinating transition. Damn it!
Most field portable phased array instruments are either 16 channel or 32 channel. Now that means you can control either 16 elements or 32 elements at one time. I think of this like the postal service. The mail person may have 128 letters in the truck, but they can only fit 16 or 32 in their mail bag at one time. There are a number of field portable instruments that allow you to use all 64 elements, say like in an A12 transducer. Today we're going to try one out. This is an OmniScan X364 and see what it looks like. I'll use a Vermon NDT 10 megahertz 64 element A12 size transducer with a 0.6 millimeter pitch. We take a quick look at beam tool. If we use all 64 elements, then the center of the beam is naturally going to be coming out in the middle of the transducer. So to make things fair, when I set up the 32 element and the 16 element focal laws, I'm going to do the same thing. I'm going to make it so that they're centered in the middle of the probe. That means on the 32 element aperture, we're going to use elements 17 to 48. And when we do the 16, we'll use elements 25 to 40. Let's take a look at the differences in focusing power when we use all 64 elements. Now, I've set up all three groups to focus on a vertical plane right at the end of the wedge. You can see that there's a stack of holes here in this phased array resolution block. So when I put the transducer down, I can line those holes right up with the center line mark that shows me I'm right on the money. You can see the 64 element is really focused. When I switch over to 32, it's still pretty good. And we go down to 16, you can see what a big difference cutting the aperture by a factor of 4 makes. Now let's put it on a real weld. This one is about an inch thick. Again, I'm going to focus on a vertical plane, but I'm going to push it about 3/4 of an inch out in front of the wedge so that I can actually see things at the root. To take a real close look at this, I'm going to do an encoded scan on all three flaws in this plate. The first one is a root crack. You can see it right there. And then after that, we'll do a toe crack and a lac fusion. Let's take a look at the root crack on Omni PC. Here you've got the 64, 32, and 16 element apertures. You can see right away, if I add just a little bit of soft gain, you can see how much definition there is in the really highly focused 64 element group. Less so on the 32, and of course, even less so on the 16 element aperture. And if we were to try to size this flaw, because that 64 element aperture is so highly focused, remember it's focused on a vertical plane, basically right through the crack, we get really, really good resolution on the tip diffractions. Taking a look at the toe crack, you can see the really well-defined tip diffraction off the top of that crack versus the corner trap signal. The 32 element is actually pretty good, and we go down to the 16 element, you can really see the difference. Lac fusion might be the most interesting one because we can actually tell the difference between the tips of the lac fusion and the planar body itself. When we move to the 32 element, we can only see one of them, and when we go to the 16 element, we can't see any of the tips at all. We get lots of focusing power when we use lots of elements, but it also costs us in approach distance. If we use all of the elements, then the center of the beam comes out in the middle of the transducer, and that puts that beam index point quite a distance from the front of the wedge. And if you try to inspect something, say thinner than this 1-inch plate, what you may find is that you just can't get the transducer close enough to the weld without hitting the cap in order to try to get that root on the first leg. So using the maximum number of elements, in this case 64 all at once, isn't going to help us in all cases. You may have to use a smaller subset of elements and use the upper portion of the transducer to push that beam index point closer to the front of the wedge and improve that approach distance. And on thinner welds, usually 16 or 32 elements will give you plenty of focusing power if you really want to dial in on something. A 64 channel instrument gives you lots of focusing power, but with great power comes great responsibility, because if you dial in a very specific focus spot and then move your transducer just a little bit or try to look a little bit deeper or a little bit shallower, it can come out of focus real fast. And for weld inspection, you're probably not focusing on a vertical plane, you're focusing at 1.5T at a true depth. So let's use that res block again. Here we'll focus at 1.5 inches or 38 millimeters down. We'll take a look at that same stack of holes. And here you can see using 64 elements, I'm just too focused. Anything at the ID or the OD of this part is going to be out of focus. So a 64 channel instrument, we can push lots of sound through a transducer, do some really interesting and high precision focused groups. Just be really careful when you have all that power that you're using it correctly. I hope you enjoyed the video. If you did, please hit the like and subscribe buttons, and thanks for watching.